O, and BX equals CY, so X and Y lie on those segments. And often this is like a spiral similarity type deal. So this is X, and you can use the compass tool. So basically, the circumcircle of AXD passes through the midpoint of the arc. Oh, it looks similar to another problem that you saw before. So by a spiral similarity, the circumcircle of AXY passes through the midpoint of arc. What am I doing here? This passes through the midpoint M of arc BAC. And another way to think about it is triangle MXB is congruent to MYC, and you can do that by side angle side, or angle side angle. Okay, so then the circle AYB intersects AXC at a point, and that's point W. Okay. Sorry, why do I keep doing this? I keep messing up. W. And O, center of this. And we want to show the radius of AXY. So we'll draw the center of AXY, which passes through M. We want to show that radius is equal to OW. But I wonder if this is a trapezoid, an isosceles trapezoid. So let's check if that's the case. This looks a little bit familiar. So yes, and I feel like I don't know exact. It just reminds me. I feel like we've done something like this before. So we have to show that's a trapezoid. And if we do that, then BA is equal to OW. So that solves the problem. How do we do that? So is AW a symmedian? I bet AW is a symmedian, right? W lies on the angle bisector. Okay, not the symmedian, but the angle bisector. Because WBX is congruent to WYC. Okay. So AW is parallel to OD by an angle chase because, wait. WXB is, I get that. WXB is congruent to WCY. Oh, yeah. Yeah, I got confused here. That makes sense. So yeah, W lies on the angle bisector. And that proves that, and then OD, how do we know OD is parallel? So OD is perpendicular to AM. So that would be why, right? Because the centers of the two circles are perpendicular to AM, and so it follows from that. Okay, so this is a trapezoid. And then can we show it's an isosceles trapezoid? Yeah. So yeah, if I draw this point right here, then obviously this is also equal to this. So EF is, okay, so EF is the perpendicular bisector, DEOF is a parallelogram. So it's a rhombus, okay. So how do we know? Yeah. So how do we know DEOF is a parallelogram? So DE is perpendicular to AY and DF is perpendicular to AX. Sorry, is it obvious that that's a parallelogram? Oh, sorry, you wrote it. DE is perpendicular to AY and OF is perpendicular to AC. Oh, yeah. I like it. All right. So by an angle chase, triangle BXY, WBY is similar to WYC. And then BX equals CY implies they're congruent. Okay. So WX equals WC. And AXWC is cyclic. That means AW bisects that. I don't even know if we end up using that in the proof, but maybe we do. Actually, I think we do. So, so basically, I use that OD is perpendicular to AM. So, like, I don't know if we need all that information, but so let M be the midpoint of arc BAC. Then basically MXB is congruent to MYC, and so that proves that MAXY is cyclic. So or by like a spiral similarity, either way. But maybe there's a better way to say this, but triangle MXB is congruent to MYC. MAXY is cyclic by an angle chase. Oh, we gotta do this. Here we go. And so OD is going to be perpendicular to AM. So OD is parallel to AW. We have that. Oops. I mixed up those two letters. And then we have that this. So EF. So what do we want to show here? So EF is the perpendicular bisector of AW. And then we're going to show it's also the perpendicular bisector of OD. So first I'm going to show it's a parallelogram. So DE is perpendicular to AY, and OF is perpendicular to AC. DE is parallel to OF. So DEOF is a parallelogram. Okay. So EF is the perpendicular bisector of both DO and AW. And that implies that ADOW is an isosceles trapezoid. And that implies OW equals AD, which is the radius of AXY. All right, sounds good. So thank you guys. I like, yeah, how we show this is a parallelogram. A lot of cool things in this proof. All right, so let's try this one. I think we might have looked at this one a little before. It looks a little tricky. So let's try this one. So this uses the Euler line. So we have a triangle with orthocenter H, and X lies on the Euler line. Let's draw the circumcircle. Okay. So we have a point on the Euler line. That's X. And then we reflect B and C over that. So that's gonna lie on the circle since this line passes through O. Maybe what I could do to make it more symmetric, I could, yeah, like that. I think that looks better. B prime X. So we see, where does B prime X meet AC, and where does C prime X meet AB? Let's see if I can also make that look better. Yeah, I want to make them both intersect the sides. So let's see. There's a good way to do that. It's going to be tricky. I'm not even sure if it's possible, but I'm going to try it. And I make them both intersect. It might just be impossible, but it's worth trying. See, if I make it flatter, do you think it's possible, or do you think it's not possible to do that? I do not know. I'm starting to think it's impossible. But let's see. Yeah, one of them will have to be an extension. Okay. So that's not the worst thing. So I'll extend AB. And this will be T. And this will be S. And the reflection of H over ST, we want to show it lies on the circle. So that's kind of interesting. Wait, is that? Yeah, that's true. Or it looks true. Oh, did you see this problem before? Did you solve it, or you read the other solutions? Okay, so then maybe do either of you remember the solution? I could just do it right now. So it looks like maybe there's some homophoty, like, because the reflection of H, like a homophoty about H takes the 9-point circle. Basically, we want to show that this point, or the foot of the perpendicular from H to ST, we want to show that that lies on the 9-point circle, right? I don't know if that's okay. Huh. And also, let's think about this. So OH, it like passes through the midpoints of these, right? So we can draw that in. Do you remember it? Okay. Yeah, if you remember it, you feel free to share it right now. I'm curious. Oh, is AH prime perpendicular to OH? No. It looked like it, but it's not. So I don't know if this would help, but these three should concur. Let A prime be the reflection of A over OH. Okay. So then we have a big symmetry here. A prime B prime cuts AB. Yeah, these points would all lie on this perpendicular bisector, right? But we already used X and Y. We already used X. Could I use a different name for the point, or I can call it X if you want, if it makes the proof easier. But yeah, Y and Z. Okay. ABC and A prime, B prime, C prime are the same 9-point circle. Okay. So let me draw that 9-point circle. But that's true by symmetry. Let me just do it this way. So 1, 2. So I, J, K. That would be the Euler circle. And it's also going to pass, if the problem's true, it would pass through D. So yeah, they have the same 9-point circle because by symmetry, just the circle in general is symmetric. Yeah. It passes through the midpoint of both AB and A prime, B prime. Because the center of the 9-point circle is the midpoint of OH. And so if you're just reflecting about OH, they have the same center and the same size, so they're the same circle. So the projections of H onto BY, YS. B prime Y, YS are cyclic. Yeah, so, oops, sorry. So yeah, if I draw all these points, yeah, they're all cyclic. They all lie on the circle. ZT. Leave out any? I mean, that one's going to be there. This one's going to be there. Okay. So that makes sense. I guess we don't know yet. Okay, so the reflection ZT. So like we don't know yet at this point. All right. Let's see. Robbie should be rejoining in just a moment. Hey, Robbie. So thanks for rejoining. So Hakan and Nguyen said they saw this problem before. In Vietnam, we have a lemma. Let H and X. Okay, let me think about this. If H and XYZ TV. So if 5 out of 6 projections lie on a circle, then the 5th also does. So basically, okay, so what is in this case, so in this case, the hexagon is BYS B prime C prime ZT. So that's B prime YS C prime ZT. And we're saying the perpendiculars from H to 5 of those lie on the circle. So therefore, the sixth one also has to lie on a circle. Let me think about that. So the projection onto BY. So yeah, let me get rid of point G for now. Let's see if it messes anything up. All right. So B prime Y would be M. Would be M. And then I'll just draw, I don't know. B prime Y would be M. And then YS I forgot where Y is. Oh yeah, Y is this point. YS would be L. And then B prime C prime. I don't think I drew that yet. But that would be projection of H on a B. That would be B prime C prime. If we project that, that would just be whatever that point is. So yeah, B prime C prime would be D. And then C prime Z would be Q. ZT would be N. Okay. And then since that's true, you're saying that B prime T projection, let's see. Or it would be S, would be the last one. It would be ST. So let's do this in order. So it would be like this, and then this would kind of be at top, and then this would be at the very top. Okay, so it would be like this. So we know that those 5 lie on a circle, and so the 6th also has to lie on a circle. Okay. So I'm just going to type this up, and then we could go back to that problem that we got stuck on and see if we can solve it. Okay. So N, Q, D, M, and L all lie on the 9-point circle of ABC. I wonder if this is just I wonder if the proof of the lemma uses isogonal conjugates. Triangle ABC. So the perpendicular from H to ST also does. And so by a homothety from H, so I'll just finish by saying this: a homothety at H with ratio 2 takes the 9-point circle to ABC, and that implies the reflection of H over ST. This is pretty interesting. I do not know this lemma, and I probably would not have thought of it, but it's really, really good to know. Have you used it in any other problem to solve? Or is this like a common lemma? Or so we did this. So it's just this one and the last one. You've used it twice. Interesting. Okay. All right, let's maximize this. So yeah, we did a lot with this diagram. So let's see what else we can do. So yeah, point. First of all, so Ravi, I don't know if you were on when we mentioned this, but I noticed that A, N, and R are collinear. So I'm not sure if that's obvious or if there's it's the same as saying that R lies on the median. So yeah, I'm not sure how to prove that. That could just drop some. This kind of reminds me of another problem that I got stuck on, I think involving MN or something like that. Let me see if I can find it. I'm searching it on my phone. Oh yeah, here it was. Yeah, so we could work on this for like another 15 minutes, but then there's another problem that I wanted to do. So we worked on it on a previous session, but I never solved it. So yeah. I don't think this is true, but let's check if MR is parallel to IN. Yeah, it's not true. Actually, I want to see if you guys can solve this other problem. I'm just going to try it out. So it looks easy, but I spent a while on it. So you have a triangle ABC, and you take any point X inside of it, and you draw the rays, and you see where they meet the sides. And then you draw the midpoints of these two. So you have this, and you draw the midpoint of this and the midpoint of this. And then you see where does, if I draw AF and AG, so AG, I just need to draw the segment, but basically you want to see where does AG cut BE and where does AF cut BC. And basically, the whole problem is just to show that this segment is parallel to AX. So yeah, it seems like a simple problem, doesn't it? But we tried it on a previous section, and I looked at it for a while, and I couldn't figure it out. So yeah, I'm curious what you guys think of this. Maybe some of you have seen it before. Or we want to show that AX is parallel to HI. F is the midpoint of DE, and oh wait, sorry. I think I see what you're saying. So did I mess up here? Oh yeah. Sorry, I think it should be this. Yeah, sorry, this is parallel to AX. HI. So F and G are the midpoints. Yeah, so I can write it out here. So let's see if I can write it without it blocking the figure. So we have a triangle ABC, and X, I'll just say X is a point inside triangle ABC. BX and CX meet AC and AB at E and B. And then F and G are the midpoints of BE and BC. AF and AG meet BC and BE at I and H. Prove that IH is perpendicular to AX, or is parallel to AX. So yeah, that's the problem. And I could put it in LaTeX if you really want. Why not? So yeah, we worked on this on another section, but we didn't solve it. And I found a lot of the statements that are like equivalent to it, but I think this might have been a riddle. I think it was a riddle on the geometry discussions and problems Discord server. Although it feels like it should be easier than that. I like that picture. FG passes through the midpoint of AX. How do you know that? Oh. That might make it really easy then. I didn't realize that. So you could project through F onto BC if we wanted. Although I think I might have actually already seen that. So yeah, it feels like there's a lot of projecting we could do. It's like we know, I think DH over HE is CI over IB. That's because the cross ratio DFHE is BIGC. So yeah, DH over HE is CI over IB. So yeah, how do you use that though? So I Like I could let AX meet BC at a point and then try to show that IHG is similar to that. There's a couple ways I could try to do it. I forgot what my original ideas were. But yeah, if DH over HE equals CI over IB, then like maybe we could do some kind of similarity, like just trying to think. Like what if we let these circles intersect? Well, that won't really do too much. Oh, yeah, I think this was my idea, but I don't know if it goes anywhere. So basically, if we draw these circles, DXC and BXC, and we let them intersect at a point, then since DH over HE is CI over IB, it's like triangles DKE and BKC are similar, and like I and H are like corresponding. That was my original idea. But so that would mean I corresponds to H. That gives us some equal angles, like BKI is going to equal angle EKH, so on. But yeah, I don't know if that does much. I think I did a little bit more with this, but yeah, I don't know if we really should need circles to solve this problem. We'll just leave it there just for the heck of it. I'm trying to remember what I did with these circles. Somehow I transformed it to a different problem. Can we project through F maybe? But yeah, onto what? That's the question. Maybe let DE and BC intersect at a point. let DE and BC intersect at R. Then RX, HI, and FG concur. Okay. Let's see. So RX, IH, and FG concur. Is that by harmonics, or so I'm going to delete these circles now because I feel like that's a little bit different. Delete. Delete. Okay. And that's because I'm trying to think about this. We need to prove K, KX, KA, KJ, KI is harmonic. Wait, are you saying you think you've solved it, or okay, so let me think through this. Sorry, you guys are really good with harmonics. So okay, so we want to show we want to show KX, KA, KJ, KI is harmonic. I agree with that. And the KX okay, so let's back up a step. So how do we know that FG, IH, and RX concur? So yeah, like how do we first prove that FG, HI, and RX concur? Maybe I'm missing something. Since RAX DB. Okay, AXDB, and then RAKFI. Okay, so I understand AXDB. Okay. All right. This is tricky, but that works. Okay. So let DE intersect BC at R. Well, so first I'll say let J be the midpoint of AX. And then by the Gauss line, J, K, and G are collinear. Or is that right? No, J, F, and G are collinear. Okay. Let BE meet BC at R. And then we have this. And then we project. So that means that R AKFI is -1. And then once we know that, that means that right? That means that FG, HI, and RX concur. Well, wait, we don't know. Okay. Sorry, let me back up a step. So we know that this is harmonic, right? AX dB. So okay, so this implies. Well, I'll write it like this: AX FI, and then from there we know that HIFG and RX concur at point K. Okay. So once you have that, then we project through F. Sorry, we project through K onto KX, KJ, KA, and HI. So KX goes to R, KA goes to this point. Yeah. So that implies that. Okay, I'm gonna write it out. So this implies that KI is parallel to AX. Since J is the midpoint of AX. Right. Let's go back to the one problem that we didn't solve, and then we will finish. All right. Very cool. So yeah, harmonics. I just got to get better with seeing harmonics like that. But yeah, you guys are awesome with harmonics. So here's the last problem we solved. Thanks for joining us, Anurag. Just a couple minutes left. So yeah, I think we've solved like 4 problems besides this. 4 or 5. So first, I wonder if we could show that R lies on the symmedian. So AN is a symmedian. And yeah, I don't know how to prove that R lies on it, but it looks like it from the diagram. All right, let's see. So in this case, G is the circumcenter of Rn. And yeah, point I, maybe I, H, and N are collinear. I don't think so, but that would be really cool. Maybe it's true. Let's see. Interesting. So A, N, and R are collinear, and it also looks like I, N, and H are collinear. That's cool. So yeah, I wonder if there's a way to rephrase this problem. So HN, so we have HN and AN, and then IR is parallel to BC. So basically it's like we have this circle through NM and 2 points parallel to BC, so that HN meets it at one and AN meets it at the other. I wonder, maybe we could like project. So we have M, N, R, and I. What if we projected all 4 of them through H? That looks kind of interesting. Maybe we could even project onto this circle right here. So HM goes to this point. HR goes to that point. And not only that, the midpoint of IR is on AB. So, or that's what we want to prove. But yeah, there's a lot of stuff going on here, right? And basically, so I mean, triangle HIR is like isosceles. So if we want to construct this diagram, really, we just draw like angle NHA is RHJ. So what we could do is we could rephrase this problem. We could basically draw the isogonal of HN with respect to AD and let it be like HR. And we could see where it meets AN. And then we could try to show, so that's like an alternative way to define R. And that might be better. So basically what I'm saying, we could kind of hide BP, we could hide CQ, we could hide this. So D, yeah, we could hide this. Yeah, we could hide a lot of things. Basically, and we could try to work backwards. So yeah, we could start with point R. And then from there, figure out everything else. Okay. So AHN is equal to RHJ, or RHD. And we let AN intersect that at point R. And then we can basically complete the figure. So we know the circumcenter of that. Well, okay, so I guess the first question is, if we define R that way, can we show the circumcenter lies on AB? So we don't need I. Don't need J. If we define R like this, can we show that the circumcenter of RMN lies on AB? So this angle equals this angle. So these two triangles are so HR is a submedian of triangle BHC. So basically we're saying let the submedians of BHC and BAC intersect at R. Yeah. Well, no, it's not a submedian of BHC. Sorry, I think I said that. Yeah. So no, this line is a submedian, but yeah, AN is a submedian in ABC, right? So isn't that, or oh no, it's not, because we don't know. Well, yeah, it is, because BFBC is cyclic, right? But oh, AR, yeah, I haven't proven that. So I noticed that AR and N, like when I had the full figure drawn out before I changed everything, I noticed that R lied on the submedian, but I couldn't prove it. So yeah, like I was thinking that could be like the next step would be to prove that. But it might be easiest just to start like this. So HN is a submedian. HR So HR is like the reflection of the symmedian over the altitude, because this is a symmedian, and then if you reflect it over AD, then you get HR. All right, I don't think we're going to solve this one today. So I'm going to stop here, but thanks everyone for participating. This was a lot of fun. A lot of very cool solutions, and we're almost at 100 videos. So next time will be our 100th video. So for everyone watching, or our 100th live stream video, I've done more than that in total. So if you want to join us in the future, feel free to email me at mgreenby801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.